Okay, yeah. So welcome back, everyone. Thanks for coming back for the second year of this. And so yeah, so like last year, we'll begin with Mario Garcia Fernandez, who will speak to us about non-Kähler Calabi-Yau geometry and pluriclosed flow. So thanks, Mario.
Okay. Many thanks. In this lecture, I'm going to talk about some joint work with Jeff Streets and Josh Jordan here in the audience. This was posted on the archive in June, and it's about non-Kähler Calabi-Yau geometry and pluriclosed flow. So the plan is to give two lectures, the first one by me and the second one by Josh. So in the first lecture, we'll talk about a very timely topic because Bismuth just got his show prize this year. So we're going to talk about Bismuth Hamiltonian metrics in this talk. And then Josh will be giving some applications of this theory to pluriclosed flow. So I would like to start with some general motivation. So if you're giving a compact complex manifold, the natural question is whether you can endow it with a preferred geometry, with a preferred metric. The type of result I'm thinking about is on the line of this result by Yau, who solving the Calabi conjecture proved that if you impose that your manifold is scalar, and furthermore that you have a vanishing first in class, then there exists a unique Kähler metric, which is Ricci flat on each Kähler class. And this Ricci flat metric is the one which uniformizes your geometry. So in the realm of Kähler geometry, this has motivated a lot of work via the study of Kähler metrics, CSCK, extremal, and so on. But if you go to non-Kähler geometry, this question is somehow too vague, because we should say something about which type of Hermitian metric are we using for uniformizing the complex manifold. So roughly, in dimension bigger than 2, this is the picture. So we have so the biggest set is the set of all compact complex manifolds. Any compact complex manifold admits a Gaussian metric due to result by Gaussian in the 80s. Then inside that one, of course, we have the set of Kähler manifolds. And then in between, we have these two kind of natural conditions. The one is the Hermitian metric, or the Hermitian form of the metric being pluriclosed, so DDC omega equals to 0. And on the other hand, we have the balance condition for the Hermitian metric. And there seems to be some tension between these two setups, because conjecturally, this is a conjecture due to Anna Fino and Luigi Bezzoni, the intersection of these two types of Hermitian metrics is just scalar. So if you have a manifold, conjecturally you have a compact complex manifold which admits both balanced and pluriclosed, then it should be Kähler. But we don't know this yet. So looking at pluriclosed metrics which are somehow canonical is something which I guess makes everyone in this audience happy, because it has to do with generalized scalar geometry, generalized Ricci flow, and so on. But on the other hand, the balance condition is somehow more mysterious and more subtle. It relates to the so-called Hall-Strominger equations. And when people typically hear about this thing, either they love it or they just dislike it. But actually, we'll have a talk about this, I believe, by Roberto in January. Actually, when you look at these two conditions from the point of view of generalized geometry, you see two types of conditions which are very different. So from the point of view of generalized geometry, the condition of being pluriclosed is an integrability condition. This is back to the work of Marco Gualtieri and Nigel Hitchin on generalized scalar geometry. On the other hand, the condition of being balanced is closely related, at least for Calabi-Yau manifolds, to the condition of having vanishing Bismuth-Ricci form. And more recently, using generalized geometry, we discovered that this condition is actually a moment map condition, has to do with vanishing of a moment map. So in this talk, what I'm going to do is to put these two natural conditions together, not the balanced one, but the bismuth-Ricci form equals to 0, and study as canonical geometries pretty closed metrics, which furthermore have bismuth-Ricci form equals to 0. So as I said, the bismuth-Ricci form equals to 0 is of course something related to curvature, but morally it's also related to the balance condition. So hopefully studying this type of metrics give us some information on how narrow is this yellow strip that I told you before, which is the intersection between pretty closed balance in the non-Keller compact. Okay, so in this talk, I'm going to take this definition of Calabi-Yau, which is any compact complex manifold which has vanishing first-chain class in second rank homology. Okay, so I'm not going to assume that the canonical boundary is true, but just this. Okay, so this is going to be my definition of Calabi-Yau. So if there are no questions about this just brief introduction, let me start by talking about this bismuth Hamiltonian symmetrics. So X is a compact complex manifold. G is going to be a Hermitian metric. And associated to this, we have the Hermitian form or Keller form, which is given by the following relation between the metric and the complex structure. So omega is a 1-1 form on X, which is real. And associated to this, I have a natural connection, which is the bismuth connection. Which is defined by taking the Levi-Civita connection plus a half of G minus H, where H is minus dc omega. Okay, so this is a connection with totally skew symmetric torsion. And the nice thing about this is that it is the only connection with total skew symmetric torsion which preserves the complex structure and also the metric. So this is a unitary connection. So this is bismuth. So this is nabla P is unitary. So because it is unitary, then it induces a natural connection on the canonical and the anti-canonical band. So induces connection on kx minus 1, which is the higher stereo power of tangent 1, 0. So here n is going to be the complex dimension of x. And now I can define what is the bismuth-Ricci form. So x g as before, Hermitian, then the bismuth-Ricci form is given by minus I of the curvature, of the bismuth connection on the anti-canonical one.
Hey, Mario, Josh asked a question in the chat.
Oh, sorry. I cannot see.
Yeah, sorry, it was just a private question. Um, no, I've heard you talk about unitary connections before. Is that the same thing as like a Hermitian connection? Is it just a different word for that? Or
Oh, yeah. Unitary means nabla j equals to 0, nabla g equals to 0. Okay.
thanks.
Okay. So on top of the definition, we say that the metric is bismuth Hermitian is the bismuth Ricci form is 0. So we say that G is bismuth Hermitian Einstein if rho B equals to 0. Okay, and this name of bismuth Hermitian Einstein will be hopefully clear through my talk. Okay, so one simple remark, one basic remark is that bismuth Hermitian Einstein actually implies Calabi-Yau with our definition. Okay, vanishing first n class in the rank commons. So let me give you some examples of bismuth Hermitian manifolds. So examples, of course, Keller Calabi-Yau is, because if we are Keller, then the bismuth connection equals the Chern connection equals the Levitz beta connection, and the bismuth Ricci form is just the usual Ricci. A more interesting class of examples in non-Keller geometry is if you take compact even dimensional Lie groups. So if G is compact even dimensional, and we take J a left invariant complex structure, which is compatible with a invariant metric, G, then this structure gives you bismuth flat, and therefore bismuth Ricci form equals 0. So this thing gives you nabla B flat and reclosed, and therefore bismuth Hermitian. Sorry, I didn't say this thing, but I'm in my definition of bismuth Hermitian, I impose reclosed. Issue. So I impose both conditions. Okay. 1 and 2. So here, the 3-form DC omega is up to a factor, the natural Cartan 3-form in the group, given by this being parametric. Okay. So there are 3 natural questions that we can ask about bismuth Hermitian metrics. So given these examples, are there any non-Keller bismuth Hermitian metrics which are not bismuth flat? Well, this may look surprising, but we don't know the answer to this question. So we do not know if there are any examples of bismuth Hermitianism which are not.
Well, I mean,
flat.
you probably also want to say that there's like not a Kähler factor or something, right? I mean, you could take like a K3 cross with a.
Yeah, of course, yeah.
But-
You want this to be
but yeah,
not a product, yeah. So if the manifold is not a product, we don't know the answer to this question. So not a product. So the second question that we can ask is, given X compact Calabi-Yau and non-Keller, which is furthermore pluriclosed, does it omit a bismuth Hermitian symmetry? And part of my talk is going to deal about, or it's going to be about giving a negative answer to this question. So question 2 has a negative answer. Okay, so let me give you some further insight on this bismuth Hermitian geometry, and then state the main theorem. And then I will, in order to prove this theorem, I will need to introduce some tools coming from generalized geometry. So what do we know about this bismuth Hermitian, and which further motivation we have for studying it, besides this thing I mentioned at the beginning? So let me give you this natural structural results. So proposition, if XG is pluriclosed, then we have the following formula for the bismuth-Ricci form. We set H to be minus dc omega, the Lie form to be d star omega composed with J. Then we have that the 1-1 part of the bismuth-Ricci form contracted with J is given by Ricci minus 1/4 H squared. So this is the symmetric tensor which appears in the generalized Ricci tensor, plus L theta sharp. This is the Lie form of G, and then the 2,0 plus 0,2 part of the bismuth-Ricci form is given by minus 1/2 d star H plus 1/2 d theta minus 1/2 of I theta sharp H. So the first thing we observe about this bismuth Hermite-Einstein matrix is that bismuth Hermite-Einstein solves a coupled system for a triple given by a metric, a closed tree form, and a one form given by these two equations equals to 0. And actually, this system appears naturally in mathematical physics because in case we formally take theta sharp to be the gradient of f, the gradient of a function, then these are, rho b equals to 0, or the equations on the right-hand side, the two tensors on the right-hand side equals to 0, give you the so-called equations of motion in type 2 supergravity. Equations of motion in type 2 supergravity. Actually, this is very interesting because if we actually impose bismuth Hermite-Einstein, then the metric and the three form solve the equations of motion of type 2 supergravity. So this is another structural result which gives us some information about this bismuth Hermite-Einstein metrics. This is already part of my work with Josh and Jeff. So suppose XG is compact and bismuth Hermite-Einstein, so in particular is pretty close and has vanishing bismuth Ricci form equals 0. Okay, this is the definition. Then there exists a function, a smooth function on the manifold such that the following system is satisfied. So Ricci minus a fourth h squared plus nabla square f equals to 0. And then this star h plus the contraction of the gradient of f with h equals to 0. And this is a very nice result. The proof uses some of the tools which appeared last year in our seminar. It has to do with the fact that a bismuth Hermite-Einstein metric, due to this formula for the bismuth Ricci form, is an steady generalized Ricci soliton. So bismuth Hermite-Einstein implies a steady generalized Ricci soliton. And now using the Perelman F functional with the three form, etc., then this has to be gradient, plus the fact that we're on a compact manifold. Okay, so this is one further piece of motivation for studying this bismuth Hermite-Einstein. Whenever we have a solution of these equations, then we are solving these equations of motion in type 2 supergravity, if you like that. It is interesting now because we have these two systems. I don't know if you can see them at once. yeah, here we have these two systems of equations. So if we subtract the two systems, we obtain now a structural property of bismuth Hamiltonian. There is a special vector. If we formally subtract the two systems, so formally subtract the two systems, then we get the following. So if X G is a compact bismuth Hamiltonian, then the vector field defined by a half of theta sharp minus gradient of F is Killing and holomorphic. And furthermore, IB is also Killing and holomorphic. So this is a pretty strong condition. And 3, a half of d theta minus IBH equals to 0. So the proof of this, I'm not saying that this is immediate, but it actually follows essentially from a previous analysis of generalized scalar Ricci solitons by Yuri Yusinowskian and Jeff Streets. So this proof essentially follows by the work by Yusinowski and Streets on a steady generalized scalar Ricci solitons. Okay, it's essentially the same analysis, but here we have further the condition that not only V is Killing and holomorphic, but also the rotation by construction. So the conditions 1 and 3 suggest that this system of equations, these bismuth Hamiltonian equations, have something to do with generalized geometry. So note that 1 plus 3 seem to point to a relation with generalized geometry. Generalized geometry. The reason this is true is because essentially 1 plus 3 are the conditions for having a generalized infinitesimal isometry. So the generalized or the analog in generalized geometry of having a Killing vector field. Generalized Killing vector field. And actually, by considering these equations in the realm of general geometry, we give an answer to question number 2 and some further applications to pretty-closed flow that Josh will talk about next week. So let me state the main theorem I want to prove, which gives an answer to question number 2. So theorem jointly with Josh, Jordan, and Jeff Streets. So assume that X is compact Calabi-Yau, and assume that there exists a holomorphic map since that this is holomorphic. Here Z is some complex manifold, compact, complex, since that df is surjective at a point and to Z is scalar and has negative first in class, then X is not bismuth Hermitians, meaning that it does not admit any bismuth Hermitians image. Okay. So the first examples we can find easily out of this result are complex surfaces, compact complex surfaces with non-negative codiagonal dimension. I will mention further examples by the end of my talk, but let me leave it here. The main message is that these bismuth Hermitian geometries are restricted naturally by thinking of them in terms of generalized geometry. And actually, what we will see is that the proof combines two things. Combines one, generalized geometry in a holomorphic setup, meaning using holomorphic Courant algebroids, and two, some geometric invariant theory. Okay, so if there are no questions,
Sorry, I
yeah,
don't
sure.
understand the C1Z condition. You're saying, like, for example, if it was over P1, this
Yeah, I'm saying that
C1
Z
is
is
negative or positive?
for P1 is positive.
Okay.
Yeah, I'm saying that if general type
And
compact
yeah, so
complex
like
manifold.
C1 positive, in fact, you will have some, like that's the Hopson.
Yeah,
case.
yeah.
Yeah, that's why I'm asking. I mean, the
Okay.
C1 of, I mean,
Yeah.
the canonical bundle for CP1 is
Yeah.
O -2. So yeah.
So like any T2 vibration, holomorphic T2 vibration over a Riemann surface, compact Riemann surface with genus bigger or equal than 2 will not have bismuth Hermitians. Something that was observed before by the behavior of the pluriclose flow in work by Jeff, but we give a proof by means of this GIT picture. Okay, so let me go then to the second part of my talk, which is holomorphic Courant algebras.
Sorry, can I ask a question?
Sure, yes.
Yeah. So, what is the example of this situation where we have C1 0 and over a base of negative C1?
Yeah. So you have a T2 vibration over a Riemann surface, compact Riemann surface of genus bigger or equal than 2.
Okay. Okay, I see.
Is it okay?
Yeah.
Okay, so let me go to holomorphic Courant algebras. So the idea, or what we are going to do, is to study Hermitian metrics on holomorphic version of Courant algebras. So definition: X is a complex manifold and then an exact holomorphic current algebroid over X is given by is a holomorphic exact sequence of the form holomorphic cotangent, sorry, holomorphic cotangent to Q to tangent, the holomorphic tangent to 0. So this map, I'm going to call it pi, and it's going to be the anchor map. And says that Q is endowed with a bracket on holomorphic sections. Q is also endowed with a holomorphic metric which I denoted by this, actually of, yeah. And then this map pi above is bracket preserved. There are these four different structures, like the extension or the holomorphic stochastic sequence, the bracket, the pairing, and the anchor map. And they satisfy some natural axioms which are formally similar to the ones in the case of smooth current algebras. That's axioms. In particular, the bracket satisfies the Leibniz rule, etc. Let me not go into the details, okay? But this is the picture. So we have a holomorphic stochastic sequence and these three types of structures. But then there is this classification theorem by Marco Galtieri, which essentially tell us how to construct these guys explicitly. So the theorem is that exact holomorphic current algebroids are classified by the first sheaf cohomology of the sheaf of closed 2-0 forms. Two-zero forms. Next. And actually, one has an isomorphism between this and the kernel of the exterior differential, just the rank differential, going from 3-0 plus 2-1 to the next degree, divided by the image of the from 2-0 to omega 3-0 plus 2-1. Okay, let me erase this thing because it's looking really ugly and place it somewhere else. Okay. So omega 2-0 close is sheaf of closed 2-0 form. So notice that because we have a 2-0 form, in particular being closed, implies the being holomorphic. Okay. So this term tells us how to construct these guys explicitly. So let me give you an example. So if I give you by the theorem by Marco, if I give you X complex manifold and I give you tau to be a 3-0 plus 2-1 form, which is declosed, I should be able to construct one of these Qs. And the way you do it is the following. You take a Q tau to be just tangent 1-0 plus tangent plus cotangent 1-0. You take then the Dolbeau operator, which defines the holomorphic structure, to be d bar of x plus c, sorry, v plus c. Equals to d bar of v plus d bar of g plus, it should be a minus with my notation, minus e v of tau. Then you take the pairing to be just the usual one in generalized geometry, b plus c equals chi of b. So here chi is a 1-0 form, b is a 1-0 vector field. And then the bracket has this form, which is kind of familiar, but adapted to the fact that we have a 1-0 types. So this is the bracket of x, y as 1-0 vector fields plus del of eta of x plus I x del eta minus IY del chi plus IY IX tau 3-0. Okay, I didn't write it here, and I should, because this only uses the 2-1 part of tau. So out of this, out of tau, which has 3-0 and 2-1 components, we use the 2-1 component to construct the Dolbeau operator, so the holomorphic structure on Q, the structure of holomorphic short exact sequence. And on the other hand, we use the 3-0 bit to cook up this bracket. And the anchor map is just the usual one. So if you want the Dolbeau operator, if you want, can be written, I should write it here, like d bar tau, can be written in matrix notation as d bar 0 and tau. Okay. So we are interested in a particular class of this holomorphic Coulomb algebra, which arise by via reduction. So we are interested in Qs obtained via suitable reduction procedure. From Is which are exact but in the smooth category. So this is an exact smooth Coulomb algebra. So let me explain this. because it plays an important role here. So I'm going to assume, or I'm going to denote my complex manifold by J. So M is the smooth manifold underlying, and J is the complex structure. So now I'm going to fix E as before. E is exact smooth current. So recall that this arises via an extension of the form cotangent E tangent 0. The tangent and the cotangent are not just the smooth tangent and the smooth cotangent bundle of the manifold. And then the basic device to produce a holomorphic Courant algebroid out of this E is the notion of lifting. Definition, this is due to Marco definition. A lifting of tangent 1, 0 to the complexification of E is a bundle inside the complexification which satisfies, well, L is isotropic to the restriction of the anchor map from L maps into the tangent 1, 0 and gives you an isomorphism. Tangent 0, 1, sorry, and gives you an isomorphism. And 3, L is involutive. Okay, this is the definition of lifting. So let me make this more explicit. So if we choose a splitting of this sequence, then we can identify non-canonically E with tangent plus cotangent, and the bracket is now determined by a closed free form. Then one can see that conditions 1 and 2 are equivalent, that L is the B field transformation of the tangent 0, 1. Let me call this L omega B, is the B field transformation via B plus square root minus 1 of omega of tangent 0, 1, where B is a real 2 form and omega is a real 1, 1 form. So this is up to 1 and 2, which are like the algebraic conditions. And then the involutivity condition, 3, is actually equivalent to H naught, which is the 3 form in the Severa class of E, determined by the splitting, being equal to minus dc omega minus dv. Okay, so this is the explicit description of this guy in terms of a splitting. Okay, so given an isotropic splitting, we can undertake a reduction procedure. Again, this is a construction by Marco in his paper about generalized scalar geometry in CMP. So we take an L as before, a lifting, and then what we do is to define the orthogonal bundle. A priori, this is only a smooth QL given by the orthogonal to L quotiented by L. Okay, so L perp is orthogonal to L. Is the orthogonal complement. Then I want to define a holomorphic structure on this guy. And for this, I use the bracket. So I define a log operator as follows: d bar L of B. So here B is some section of tangent 0, 1 applied to the class of S. In this quotient, this is defined as the bracket of B tilde S mod L. We want the class of the bracket, of the Dorfman bracket. Okay, and B tilde is the lift, the unique lift of B to L, because in the definition, recall that we impose that L is isomorphic to tangent 0, 1 via the anchor. Now, the fact that this dot operator is integrable follows essentially from the fact that the bracket, the Dorfman bracket on E satisfies the left full. This is the proof. And now one can check that on holomorphic sections, one actually has a well-defined bracket. So the bracket of the class of S1, class of S2 is the class of the bracket of S1, S2, or if you want, yes, S1, S2 mod L. Okay. And again, this is an exercise to check that this is well defined on holomorphic section. Okay, so this is just the formal definition of this reduction. Let me give you an actual reduction in more explicit terms. Okay. So lemma, given L and splitting, sorry, a lifting of tangent 0, 1 as before, e to the b plus square root I omega tangent 0, 1 inside the current algebraic tangent plus cotangent complexified for some freeform H naught. So here I'm fixing H naught, a three form on X, which is real, which defines the Dorfman bracket. And this is a lifting, giving L a lifting. Then the reduction of E tensor C, so tangent plus cotangent tensor C via this L is isomorphic to the holomorphic current algebraic determined by the 3, 0 plus 2, 1 form 2 square root minus 1 del of omega. So here I should make a comment. So recall that before, so in Marcos term, so this is a remark in the term above about the classification, we needed tau 3, 0 plus 2, 1 form, which was declosed. And then we were constructing this particular model given by tangent plus holomorphic tangent plus holomorphic cotangent, with bracket and with bracket and dot operator given by the 2, 1 part and the 3, 0 part of the form. So here, what I'm saying is that my tau is 2 square root minus 1 of del of omega, and this is declosed because the lifting condition in particular implies that H naught equals minus dc omega minus dB, which implies that ddc omega equals to 0. So the omega needs to be ddc closed, and therefore this tau is declosed. Okay. And in case you forgot about how you construct this Q, let me just go up for 5 seconds, so you can stare to this construction. So essentially, the most important thing that you should remember is that Q tau as a smooth tangent is tangent plus holomorphic tangent plus holomorphic cotangent, and the Dolbeau operator has this form, and therefore it defines a holomorphic extension. Okay, and here it should be 2, 1, by the way. Okay, so these are the ones which are obtained by reduction are particular because the tau has no 3-0 component, and furthermore the 2-1 component is del of something, is del of a real model. Okay. Any case, so we have this crash course on holomorphic Courant algebroids, and now I go for the main thing I'm interested in, which is the study of generalized Hermitian metrics. So what are these things? So I'm going to take as before E exact smooth over M, and I'm going to take my complex manifold to be MJ. So this is a Courant algebra before. So if you want to think of it as tangent plus cotangent with a bracket defined by some closed 3-0 form, which is real. Okay. And then we can consider in this guy generalized metrics, which I hope is familiar to everyone. So consider a generalized metric on E. Nice metric, which I'm going to regard as a decomposition into B plus B minus, such that the pairing restricted to B plus is positive definite, and the rank of B plus is, yeah, I don't need to say anything because I'm the exact case. Okay, yeah, so this is generalized metric. Then this structure determines an isotropic splitting of E, and therefore a particular way of viewing E as tangent plus cotangent for a particular choice of closed free form H, and then with the canonical pairing and uncommon. And in this splitting, my generalized metric is very simple. It's just B plus minus G of B, or B in the tangent, and G is a Riemannian metric. Okay. Now, with the thing we said before, there is a natural compatibility condition between generalized metrics and the complex structure. And this leads us to pluriclosed metrics. So definition, now I have my E over X as before. And I have a B plus, a generalized metric. On E is J compatible if L defined as the set of are the set of elements in B plus complexified, which project to the tangent 0, 1 via the anchor map. This is supposed to be a pi, but my pi's look like H's and it's horrible. If this guy is a lifting of tangent 0, 1. Okay. So now this is the basic lemma. B plus is J compatible if and only if one, the metric determined by the generalized metric is Hermitian. This is just a manifestation of the fact that your L is isotropic, and therefore G has to be of type 1, 0 plus 0, 1. And 2, H, the free form determined by the generalized metric, is precisely minus dc omega, where now omega is the Keller form of the Hermitian metric. So omega is G J. Okay. So the proof is very simple, and it amounts to write down what is this L explicitly. So just note that you can write your L in this setup in the splitting in the particular splitting determined by the generalized metric. L is just e to the square root minus 1 omega of tangent 0, 1, and then you apply the previous result. Okay, so in particular, this is the first comment. This is about the proof. The second comment is that if B plus is J compatible, then G is pluriclosed. And the other thing is, and there is a converse to this, in the sense that if you are giving a pluriclosed metric on a compact complex manifold, or in a complex manifold, you can construct a Courant algebroid given by taking H minus dc omega with a lifting, with a generalized metric, which is J compatible. Okay, so given a pluriclosed metric, you can construct a J compatible generalized metric on a suitable Courant algebroid determined by the torsion. Okay. Okay, so here is the main definition that we're going to use now. Definition. B plus me J compatible generalized metric as before. then the associated generalized Hermitian metric on QL, because J is J compatible, it determines a splitting. Recall that QL is simply tangent 1, 0 plus cotangent 1, 0 with the d-bar operator twisted by 2 square root minus 1 del omega, in this case, is given by the following. G of the class of S1 class of S2, this is in the description of QL as a quotient, is given by minus 2 projection of S1 to the B minus projection of S2 to B minus and product. And I have to take a conjugate here. So let me explain this. What do I mean? Let me explain. So here the SJs are in L perp quotient by L, which is by definition our QL. Let me be more explicit, okay? And try to explain you this definition, why this is natural, and then try to make it more explicit. So why this is natural? So the first remark is that this is very natural because L perp quotient by L is canonically isomorphic via the projection into B minus. So B minus is the projection from E to B minus with B minus tensor C. So the orthogonal complement to B plus complexify. So what I'm doing with this definition here is just taking the C-linear extension of the metric on B minus and then taking the natural Hermitian metric as it is. Okay. And this is the first comment. My second comment is just an explicit formula. So this is why this metric is natural. The second one is why is it computable? Well, because QL, I told you that this is Q2 square root minus 1 del omega, but this is as a smooth bundle. This is just tangent 1, 0 plus cotangent 1, 0. And therefore, we can write the metric in this splitting. But in this splitting, the metric is very simple. It's just G, 0, 0, G minus 1. There is a factor of 2 which appears that I'm going to ignore. Okay, so this is the tangent 1, 0 bit, and this is the cotangent 1, 0 bit. Okay.
Mario, can I ask a question?
Yeah. Yeah, sure.
I guess right. So for standard like Hermitian geometry, I mean, like as tensors, it's very easy to sort of jump between like the Riemann metric, the Kähler form, or like the genuine Hermitian metric. I guess, is it possible here? Is it easy to sort of build or canonically build like the generalized Hermitian metric out of the generalized Riemannian metric?
Oh yeah, this is what I'm saying here. This is what I'm trying to say, that
you're literally just restricting it to that sub bundle, basically.
Yeah, what you do is you take the natural metric in B minus.
Yeah.
You flip a sign, but it doesn't really matter because you could take it negative, definitely doesn't matter. You take the natural metric in B minus, extend it C-linearly to B minus tensor C, and conjugate on the second entry. So this is like the natural Hermitian metric on the complexification of B minus. It's got given by the general.
Okay. Yeah.
Yeah.
Thank you.
Yeah. Okay. So we have this natural class of Hermitian metrics, and now we can ask ourselves whether we can compute the churn connection for this. And this is my next subsection, which I call it Bismuth's identity. This is just about what is the churn connection for G. So notice that, for example, from this point of view, which is very explicit, and this is what most of people like, from this point of view, the metric is very simple. It's just diagonal, but the Dolbeault operator is twisted, and this makes a difficulty in determining what is the churn connection. Okay, but what we're going to use is this description here, so the first description, and the abstract definition of the holomorphic Courant algebra by Marco Gualtieri, and then the churn connection will pop up very naturally. Okay, so this is a proposition in our work, in our paper. So say that we have a P plus any a generalized J compatible generalized metric as before. Then via the identification of QL with B minus tensor C, which is given by projecting into the minus, orthogonally projecting into the minus component. The churn connection of the generalized Hermitian metric G, which I defined before, and you have it right here. Is the following as the natural formula: dg of B acting on S. So I'm identifying QL with B minus tensor C. So S is just B minus. This is just P minus, so the projection into B minus of B plus GV. This is the natural lift of B, which is a vector field on the manifold to the B plus. So here B is just an ordinary vector field on my manifold. And now I take a bracket with S. And this expression is just using the Dorfman bracket. More explicitly, because this looks a bit abstract, more explicitly, via the identification of B minus with B minus GV with B in tangent, we have that dg equals to the C-linear extension of nabla minus. which is the Levi-Civita connection minus a half of G minus 1H, where H is minus DC omega. This appears naturally in the literature in several places, mainly in mathematical physics, and people often call this the Hall connection. And it's very nice because I think it hasn't been appearing before. It has not appeared before in the literature about generalized geometry in relation to pluriclosed metrics. Is somehow something which naturally pops up by this construction of holomorphic chronometric, but it's not. And actually, sorry, because this is a bit big. Let me try to compactify it. Oh, I need to take it bigger. Yeah, maybe now we can see it. No, we can't. In any case, let me try to compactify it more. I tend to write big. This is bad for. Okay. Yeah. Yeah. What I wanted to say is that this calculation of the Chern connection pops out just naturally from the construction of the holomorphic Courant algebra. So what do we need to check for this to be the Chern connection? Well, this DG needs to be compatible with the unitary structure, so compatible with the Hermitian metric. But this definition here is just the C-linear extension of something which is compatible with the metric on B minus. Therefore, its C-linear extension is unitary. There is nothing to do. There's nothing to check. So the second condition we need to check in order to prove that this is the Chern connection is that the 0,1 bit of this guy coincides with the double operator of QL. But this is the way we're defining it. This is just the way we have defined it. Okay. And if you now calculate what is B plus GB on a 0,1 vector field, this is just e to the I square root of omega, acting on omega. And this is precisely the lifting of tangent 0,1. Okay. So the proof is a line. From the previous construction. So the proof is follows from nabla minus being G orthogonal, which is the same as saying that this operator here, P minus bracket, is orthogonal. Plus the abstract construction of the double operator. On QL. So if you, let me just recall for you this definition, which was a way before. So the definition was this one. It just uses the lifting to tangent 0,1 and the bracket. Okay. So essentially, this is the proof. Let me not go into more details, but this is important. Okay, so this finishes this part. An important, or maybe a historical remark, is that this was already proved by Bismuth in the 80s. Proved by Bismuth in his seminal paper in Communications in Mathematical Physics in 86 about the twisted Dirac operator. Okay, and he uses, of course, he doesn't talk about generalized geometry, but he yeah, sorry, yeah.
It's in Analan, I think. I think it's like
Analan. Yeah, you're right. Sorry.
88 or 9 or something.
Yes, sorry.
Or
yes,
anyways.
This is in math.
It's the index theorem, not non-killer index theorem.
Yeah. So he didn't write it down in terms of this generalized geometry, but he wrote it down in terms of the explicit description of Q as tangent 1,0 plus cotangent 1,0. Okay? And he wrote this. He used this explicit formula for the Chern connection instead. Okay. So far, so good. And this is from 89, actually, not from 86. Okay. Right. Yeah. I was going to say something, but then it's going to get bored. It's going to get boring and nasty. So I'm going to skip this thing. Let me just say something. We have defined in some sort of ad hoc way, by means of a generalized metric, some holomorphic Coulomb algebroid endowed with a metric. And for applications, for Josh's talk, for next talk by Josh, it is important to fix some background holomorphic Coulomb algebroid. Need a fixed holomorphic current Q naught. And because we need this background Q naught, it is important to define generalized Hermitian metrics which are not related to the given Q. So it is important to unrelate the generalized metric to the holomorphic Coulomb algebroid it lives with. Okay. So there is an abstract definition which comes from or is motivated by my work with Roberto Rubio, Carl Tipler, and Carlos Sabasi on canonical metrics on holomorphic Coulomb algebroids in relation to this Schrödinger equations. But in the end, the point is that you end up with a definition which matches a formula which was written previously by Josh Jordan and Jeff Streets in previous work, and is a very nice object to consider. So the thing is that need a fixed holomorphic Coulomb algebroid and some moving generalized Hermitian metric. And in order to untangle these two objects, which in our construction are intertwined, what one does is to consider three things. You just consider some generalized metric on some smooth Coulomb algebroid, which is J compatible, and then some phi, which goes from the reduction via this B plus of E tensor C to the Q naught. And this is an isomorphism of holomorphic Coulomb algebroids. So this is an isomorphism. In the end, this turns out to be explicit, written down in terms of explicit tensors. And you end up with some metric, which is now of the form G plus beta, so beta minus beta G minus 1, beta G, G minus 1, where beta is a 2-0 form on X. this beta is essentially the isomorphism phi, and it has to satisfy a relation between h naught and dc omega. More explicitly, d of beta is tau minus partial omega. Okay. And this is the type of metrics that one. So essentially, this is the generalized metric I told you about before in QL, and you push it forward via the isomorphism. Okay, and the isomorphism is the 2 0. Okay, Josh will tell you more about this thing in next talk. So let me move on. So we have this proof, this bismuth identity, which identifies the Chern connection. Therefore, it is natural to ask what is the condition of being Hermite-Einstein for this metric. So this is the last part of my talk, which is about bismuth, Hermite-Einstein, and slope stability. So let me start stating this result, and I will give you the proof because it's simple. Again, this is in our work. As I said, it essentially follows from this identity by Bismuth, even though he didn't write it down explicitly. And so let XG Bismuth Hermite-Einstein. So recall that this means that DDC omega is 0. So my Hermitian metric is pretty close, and the Bismuth Ricci form is 0. Then the generalized Hermitian metric G, given by this formula, on QL, on Q, now I give you explicitly what is this guy. This is the holomorphic Coulomb algebra given by 2 square root minus 1 del omega, which as a smooth bundle is just tangent 1, 0 plus tangent 1, 0 dual. Recall that this has a twisted divar operator given by this 2, 1, 4. Is Hermite-Einstein. Meaning that the curvature of the Chern connection of this G, which omega n minus 1 equals to 0. And here omega is the Hermitian form determined by the same metric G. Okay. So this condition, which looks like the usual Hermite-Einstein condition, is really coupled. Is intertwining the Chern curvature of G with the omega. Okay, and this is the catalyzer, the key result for our obstruction that I mentioned at the beginning of mine, and also essentially the key for the interpretation of pre-closed flow as some sort of Donaldson flow for Hermite-Einstein metrics. Okay, let me give you the proof because I think it's important. So the proof is very simple. Recall that we can identify the Chern connection with nabla minus, actually with the C-linear extension of nabla minus. What nabla minus is Levi-Civita plus a half G minus 1 DC omega. Okay. And now there is this magical formula which tells you that G of the curvature nabla minus of B1, B2, B3, B4 equals, because DDC omega equals to 0, to G of R nabla bismuth B3, B4, B1, B2. So if you see this formula, if there were no torsion, it's just the first Bianchi identity. I mean, it's not, it's essentially the first Bianchi identity. But here we have connections with torsion, but the torsion is closed. And then we have this natural symmetry between the two entries. Okay, so the proof from this identity, the proof now follows by definition of the Bismuth-Ricci form. So the proof now follows from the following formulas. Which are basic. So on the one hand, we can calculate rho B of BW summing over an orthonormal base. And here I should put a J, sorry. This is J, EJ, comma, EJ. On the other hand, I can calculate R nabla minus, which omega in minus 1, also by summing over an orthonormal base, but in a different entry and for the connection nabla minus. Sorry, this is R nabla minus EJ, J, AJ. Okay, and that's it. So combining these two identities, these two definitions with this magical formula for which relates bismuth with Hall connection, then you get the result. Okay. Are there any questions? Okay, so if not, let me go for the punchline, which is the following term. Yeah, sure, sorry. Yeah.
FG is just the two form here.
FG is the curvature of the Chern connection of G. So G is a Hermitian metric on a holomorphic vector bundle. So it's just the usual Chern connection. Is the curvature of the usual.
Okay, so it's still endomorphism valued.
Yeah, it's a two form with values in endomorphisms of tangent 10 plus cotangent 10. Yes.
I see. And it's the curvature of the thing that you just explained.
Yeah, it's the curvature of G. In this holomorphic vector bundle, which has a twisted D-bar operator. Okay.
Okay, thanks.
Good. So from this, we can now prove this theorem, which is essentially what I started at the beginning. Theorem. Jordan. Streets. So X is compact and Calavillao. Meaning that the first n class of X is 0. Assume that X admits a bismuth Hermitian symmetric G, which recall is just pretty close plus bismuth Ricci form equals to 0. Then for any holomorphic map F from X to Z, some other compact complex manifold, such that df is surjective at a point one has the following inequality. Okay, let me, again, I'm writing too big, so let me try to reduce this. Higher. One has that the pullback of the first in class of Z times A is bigger or equal than 0, where A is the class of omega tilde to the n minus 1, where omega tilde is the unique Gaussian metric in conformal class. Of G. So, okay, I didn't write the cohomology. This is in Apley cohomology, right? So omega tilde is DDC closed. Omega tilde n minus 1 is DDC closed. So this is in the Apley cohomology of the manifold. And furthermore, and this is kind of cool because it recovers some classical result. Furthermore, if we take F to be the identity, then equality implies scalar, based that G is scalar. Okay, let me try to again. Maybe it's okay. Okay, any questions about the statement? So we have a compact Calabi-Yau vanishing first in class. If we assume that we have a bismuth Hamiltonian symmetric for any holomorphic map to a compact manifold for which df is surjective at a point, then one has this inequality, where the first in class is regarded as in Bochern cohomology, and A is the cohomology class of the unique Gaussian metric in conformal class. Let me comment on the proof.
Can you please repeat the identity? What is the statement when F is identity?
Oh, yeah. If we take F to be the identity, if this thing here is an equality, then G needs to be scalar. G is scalar.
But then C1 is 0.
Is zero in the rank
Okay,
homology.
I see. It's trivial. You say that
Yeah,
if the degree of a flat bundle is 0, then must be Keller, of course. Yes, that's trivial actually.
So the first in class, I'm only assuming that the first in class is 0 in the rank homology, but not in both term homology. And this is just the fact that if you have a, I mean, I will comment on that. This follows from a result by evolution.
But this
follows that.
C1, the C1 ZA is just the degree of C1. The degree of line bundle was defined by Duchamp.
Yeah.
Yeah. So it's yeah. I understand why it is true. So
Okay.
thanks.
That's fine. Okay. So the proof is by application of the previous lemma and the Donaldson-Lembedjau theorem and its extension to Hermitian manifolds. So the proof is by Donaldson, Uhlenbeck-Yau, and Lee-Yau, Buchdahl in the case of Hermitian manifolds. I never know how to write Buchdahl. And previous lemma we have that Q2 square root minus 1 del omega, which is recall is tangent 1, 0 plus cotangent 1, 0 with this twisted bar operator. This is a slope stable because we have a Bismuth-Hamilton-Einstein. The generalized Hermitian metric is Hamilton-Einstein, and therefore this guy is slope stable with respect to omega tilde n minus 1n, where omega tilde is Gaussian. And now the other observation is that with the hypothesis that we have, given now f from x to z is in the statement, we can construct a subsheaf of Q. We have that the pullback of the cotangent of Z, which fits naturally, has a natural map to the cotangent of the manifold X. And the assumption on the differential tells you that this is actually a subsheaf. And of course, because we have a holomorphic Courant algebra, this fits inside Q, 2 square root minus 1 del omega. Okay, so now from this subsheaf, you just calculate the slope. And you just have to realize that the slope of this guy, the degree of this guy is 0, because this is orthogonal. So this finishes the proof. So now, well, let me know, are there any questions? What is? If not, I give you.
Could you give more detail?
Sorry?
Could you give more details on?
Yeah, sure. About which part?
I guess how the slope calculation gets you to the final thing.
Yeah. So the slope of for this, the slope of f star T star set is just the first in class of the determinant of this thing times A, which is the class of the Gaussian metric, quotiented by the rank, which is going to play no role here because the dimension of set is going to be no role because the degree of Q is 0. And this is equal to the pullback of the first in class of set with a sign divided by the dimension of set times A. So now because this Q has 0 degree, the inequality slope gives you the claimed condition on D.
And C1 it's not a Durham, it's in the bot churn.
No, C1 is in both churn because A is only in Naples. So you have the class in Naples homology of the Gaussian metric in the conformal class, of G. Okay. So this is the way you measure the degree in a Hermitian line. If you have a solution of Hermitian Einstein with some Hermitian metric, the way you measure the slope and the degree is you consider the unique Gaussian metric in the conformal class of G. Consider its Apli class and pair that Apli class with the class in Bochern homology of the determinant.
And what does the Donaldson-Uhlenbeck-Yau give you?
It gives you that for any subshift, you have that the slope of the subshift has to be smaller or equal than the slope of the band.
That's the result that tells you that Einstein condition implies that it's semi-stable with
this. Yeah. So this is sorry, I started saying that by. Yeah. Okay. This is okay. Yeah. So if this were Keller, this is the old classical result. We just tells you that if you have Keller Einstein, the tangent bundle is stable, right? But here you have a non-Keller manifold, and then you have a complicated. The tangent bundle is replaced by tangent plus cotangent with a twisted operator. And the natural Hermitian metric is played by this diagonal metric. And this is what is Hermitian saying. But now you have to measure the slope with respect to this Apli class instead of the usual round.
I see. And can you say again about that comment when you have the identity?
Yeah. Okay. So in case we have the identity, okay. So if F equals identity and we have equality, then because the bundle is a slope stable, it has to be a split. This is as holomorphic vector bundle. This is tangent 1, 0 plus cotangent 1, 0. But what is the second fundamental form for this QL? This is precisely del omega. So the second fundamental form has to vanish. And therefore, del omega is 0. So omega is scalar. Okay. But the second fundamental form is precisely, essentially, del of omega. So this being split tells you that this is 0. This is something that was known before, as Besti was commenting, because if you have this mode Hamiltonian insane, then this implies that the Chern curvature has to be bigger or equal than 0. And then if it is bigger than 0 at a point, the metric has to be Keller. This is some result by evolution in some, and maybe Jeff knows the reference, I don't know.
Maybe not exactly, yeah. But it's in our paper. I forget.
Yeah.
Exactly. Also, what do you mean by second fundamental form in this context? What does it mean?
Oh, if you split your bundle as a smooth complex vector bundle in a direct sum, then oh no, sorry. What I'm saying, if you have what I'm saying is that if I have a holomorphic vector bundle Q and a subbundle F, then the second fundamental form measures the difference between the Chern connection and I have a Hermitian metric.
Okay,
G,
yeah. This
Hermitian.
definition, I guess I know, but then what's like you just, in this example, like what's the subbundle? Or
is the holomorphic cotangent bundle.
Oh, okay. Okay. Sitting inside QL.
Yeah.
It's like okay, yeah, okay.
Yeah, essentially,
Yeah. I see.
So I think essentially you can identify. I mean, what if you in this when you have a slope stable bundle, which has when you have a slope polystable bundle which has a subsheet with where the degree equals the degree of the bundle, then it has to be split. And then what you do is you express the double operator in terms of some off-diagonal part. This means that the off-diagonal part is 0. So essentially, this is what I mean. I'm not sure if using second fundamental form for this is correct, but I think.
Okay. No, yeah, I think I understand. Yeah.
Okay. So now just to finish, let me in a couple of minutes comment on 2 examples. When I comment by words at the beginning. So example 1 is really a class of examples. You have a X compact complex surface, which is a T2, a holomorphic T2 vibration over a Riemann surface with genus bigger or equal than 2. Compact. Riemann surface. Genus of set bigger or equal than 2. Then you have that the first chain class of X is 0 in the RAM if the T2 vibration is non-trivial. If X is, another way to say it is if X is non-Keller. And applying the previous result, we get that no X admits no bismuth Hermitian matrix. And the way to prove this is by brutal I mean, yes, taking, let me put it this way. You just evaluate in any possible positive apply class. So the statement of this term tells you that this inequality here needs to hold for some positive apply class, meaning that in particular, if for any apply class this inequality does not hold, then X does not admit any Bismuth-Hamiltonian symmetry. Okay. So what you do is just to evaluate this in any positive apply class by.
So I'm sorry, I got confused.
Yep.
This example, it's so X is a complex surface.
Yeah.
So it's fibers over a homogeneous surface, you say, and
yes,
you want C1 to be. So is this Epley C1 or the drum C1? I
this
think
is the drums.
Okay, so then by classification, we know that the only one is the Kudera-Thurston, and then it doesn't fiber over a Riemann surface of homogeneous, this one. Or I'm getting something wrong. I mean, your definition of C1.
Yeah, so there's the general result which says that if you have a T2K, in particular T2 fibration over a Kähler manifold, then if the fibration is non-Kähler, if the fibration is non-trivial, then the X is non-Kähler, and furthermore, you have a explicit description of the cohomology of X. So essentially, it's the quotient of the cohomology of set by the two generators of the two fibers. So what you're saying is that there are no.
No, I'm just getting confused how you get C1 equal to 0 from that. From this.
Yeah, because so this is I don't remember the reference. So in a let me check this thing.
Oh, I see. So you will have S1. Oh, yeah, it's covered by S1 times something, and perhaps this will. Okay, yeah, never mind.
Okay. Yeah. So the point is that this so you can calculate the rank cohomology easily of this X, and it's the quotient of the cohomology of set by the two generators of the two circles. And because you are on a Riemann surface, then there is no first in class.
Yeah, I see the argument. Yeah, thank you.
Okay. So X admits no Bismuth-Hamiltonian symmetric by evaluation of this inequality. So let me call this F. Of this quantity for any A positive apply class. So essentially, if you have a positive apply class, this quantity is going to be minus the integral over X of the pullback of omega set, where this is I don't know if I'm putting the signs right. This is going to be minus the integral over X of the pullback of the negative definite of the Kähler metric on set with constant scalar curvature negative, which some omega. So therefore, this is going to be bigger or equal than 0. So this is going to be always negative. Okay. It just follows from this. And I should mention that this was already observed in work by Jeff Streets on pretty close flow. So what Jeff proved is that if you have a compact complex surface with non-negative code-area dimension, which is all arises as finite covers of these guys in this example, then pretty close flow collapses the fibers essentially, right? Is it? Am I correct, Jeff? And you get Gromov-Hausdorff convergence to
well, like in the T2 invariant case, yeah. Like
okay.
assuming torus invariance, yeah.
Okay, yeah. Well, anyway,
and yeah, you can prove in general, like the area of all those fibers will go to 0. Yeah.
Okay, so yeah, but morally, is at least it was already in Jeff result, because if the precursor would converge, it should converge to Bismuth Hamilton instant, and he was observing that this was not the case. It was collapsing the fibers to 0 up to the negative curvature metric on the base surface. And the second example, just to give you an example in higher dimensions, very briefly. And the second example is by taking a set to be a degree D hypersurface in P3. With the bigger or equal than 5. Then you take a T2, you take X to be, let me write this way. You take X to be a T2 vibration over Z, which is determined by the first in class of Z and some class alpha in the rank homology, integral homology, intersection with H11 of X. H1 of Z, sorry, this is Z. Again. Right, and then what you do is to prove that there are natural conditions under which X is pretty close. So this is a result by Grancharov. Boom. Take now oh, by the way, sorry, I didn't say that. The fact that this X is generated by the first in class and class of alpha tells you that the first in class of X is 0. Because in the rank. Because the rank homology of X is identified with the quotient of the rank homology of Z by the two generators. Now you take omega to be the pullback by this map of e to the u omega Z plus theta 1 with theta 2. These are curvatures on the two circles, and omega Z is some scalar metric on the base, and then omega is pretty closed. If and only if for suitable u, I'm not setting this properly. With these ansatz for omega, we have that one can prove that X is pretty closed. If and only if the class of omega Z squared equals minus the class of alpha times the class of alpha. So essentially, you just need to solve this condition in cohomology. So you just need to find some 1-1 class, which is integral, the class of alpha, whose minus squared is the square of a Kerr class. And yeah, this is just an easy consequence of Kirchhoff's formula for the Hodge numbers of a degree, the hypersurface, plus topological facts about the surface. So what is the signature in the second cohomology for the natural round pair? So this gives you a further class of examples where you can prove that there is no bismuth-Hamiltonian symmetry. And the argument is exactly as before, just by evaluation of the inequality on any positive Ripley class. Okay, so I guess I'm done. Sorry for the time. Yeah, thanks.
Yeah, thanks, Mario.
Can I ask a question?
Yeah,
Sure,
please.
yeah.
Yeah.
This is about your first example. I think, if I'm not mistaken, there is probably an alternative argument for complex surfaces that you cannot get on those examples, even zero bismuth scalar curvature.
Yes.
Just by some vanishing plurigeneral result.
Yeah. I think yeah.
So
In the end.
Yeah.
Sorry.
Well, sorry, I didn't. But yeah, for complex surfaces, I mean, it's even worse. Like you have a complete classification. You know that this Hopf surface is like the only example. I guess it's just it just illustrates in complex dimension too. It just like is a more simple illustration of how you can get the non-existence, but then in higher, but it's not really a new result. But in higher dimensions, it's a new result.
Yes.
There's no obstructions in higher, no previous obstructions in higher dimensions. Yeah.
I had kind of it's a little far afield. But so it seems like in the formula you wrote for the Chern connection, it seems like that extends pretty quickly to like a generalized connection. But there's like that non-uniqueness result for the torsion-free generalized connections.
Oh yeah, that's interesting.
Yeah. So I was just wondering if you had any thoughts on that, like why it
No,
seems
but it's
canonical.
very that's intriguing. So for example, let me say what I think is true. I think how did we prove that Hermitianism for the generalized metric implies bismuth and it implies how do we check that Hermitianism for the generalized metric implies bismuth Hermitianism? This is by direct calculation of the bismuth Ricci form, or if one of the second Ricci form. So let me go to this formula. So the point is this formula here, right? I believe this formula has a proof in generalized geometry. And the proof then that Hermitianism for the generalized metric implies bismuth Hermitianism is like this. Is immediate. But the proof of that, I think, uses torsion-free generalized connection. So there is a sort of Bianchi identity for torsion-free generalized connections, which specifies to it. And in the end, you don't need the other bits. So a torsion-free generalized connection has 4 bits, like derivatives of plus with respect to minus, minus with respect to plus, plus with respect to plus, minus with respect to minus. In the end, this formula here is only seeing the plus, minus, minus, plus parts. But I think it's a manifestation of some sort of Bianchi identity for torsion-free generalized connections, which I don't know how to prove. But that will be extremely useful.
But is it true that like the churn connection associated to this like generalized Hermitian metric does define a generalized connection in your sense?
Yeah, but
In some
so
ways.
the point is that the two operators which appear in this picture are just the mix operators, the
Oh,
plus minus and the minus plus.
I see.
The
Okay.
plus minus appears as the bismuth connection, which is the natural connection in the plus part, and
Yeah.
the minus plus and the other guy appears as the churn connection of this guy, which is the hot connection. And somehow the other two bits are not there. I don't know if maybe using Marcos' connection, the one that he calls generalized bismuth connection, which has torsion. Maybe this gives some further.
Sure. Well, but then you're still just
insights.
kind of picking it as opposed to sort of.
Yeah.
But yeah.
But I think my thought on this is that there is a general formula for torsion-free generalized connection, a general Bianchi identity for torsion-free generalized connection, which specifies to this formula here in the square, and which gives you immediately that that Hermitian implies, or Hermitian is equivalent to bismuth Hermitian.
I see. Okay, I don't know, anything else? Yeah, okay, thanks, Mario. That's great. And so, yeah, so next week we'll have Josh.